welcome to today's session. As we discussed in the last module, we are going to look into transistor level design and sizing of transistor for a two-stage op-amp that we have been working on. And in the very beginning of the sessions, we looked at the high level specifications of the system, which is biomedical front end acquiring a neural potential data. And we derive certain specifications for the front end amplifier, for example, in terms of bandwidth, gain, the precision required, accuracy required, and so on. So we'll revert back to that discussion, and from there we'll try to link the transistor level parameters, the transistor dimensions. Now we have all the other information, all the other recipe required to do the sizing. We have the noise analysis, we have the frequency response, we have the compensation, stability, all that coming into picture. Also other considerations related to signal swing, etc., that we are also aware of. So we have all these recipe. Based on that, we can look at the transistor sizing required to meet the high level specification of the amplifier. So let us get started. So let us recap very quickly the signal characteristic that we were looking at. So we are looking at the neuropotential signal, which is having signal content say from 0.5 hertz all the way to say a few hundreds of hertz, basically 100 hertz. And in order to save this signal, which is having a very small magnitudes, 10 microvolt to say 100 microvolt, in order to save the corruption of this signal from noise, we discussed the concept of chopping, and we considered shifting this signal to a high frequency with the help of a chopper. And we discussed the concept of 1 upon f noise and how chopping can help us in mitigating the 1 upon f noise effect. So through design and analysis, we can of course try to push this 1 upon f corner frequency towards lower side, and we have seen that in the different amplifier topologies that we have discussed how the 1 upon f noise depends upon the transistor sizing, and of course the bias current. So one target can be that for a given bias current limit that you have, for a given current budget that you have in the circuit, you can try to push this 1 upon f noise corner towards as low frequency as possible. And likewise, another target happens to be to minimize this white noise level for the noise spectrum. And once we have done that, then we decide the chopper frequency fc with which we are going to multiply the signal, and we assume that fc is sufficiently higher than this 1 upon f corner frequency, maybe at least 4 or 5 times higher than the 1 upon f corner frequency, so that the input signal is sufficiently isolated from this 1 upon f noise spectrum. And in our case, if we are say able to push down the 1 upon f corner frequency to say 100 hertz, and then assume that the fc should be at least 5 times, or say to be more conservative 10 times higher than that, then you have a chopping frequency of 1 kilohertz available. So suppose 1 upon f corner frequency is 100 hertz and the chopping frequency is accordingly 1 kilohertz and an order of magnitude higher. This is a little bit more conservative. I can go for slightly lower also, but let us target a little bit conservative values. So let us keep the chopping frequency to be 1 kilohertz. So now this is the chopping frequency for the amplifier. From there we need to look at the amplifier bandwidth required to support this chopping frequency. So once again, if I look at the chopping behavior, ideally if I do mathematical modeling, the chopping would imply multiplying of an input signal with plus minus 1. So this is plus and this is minus 1, and you have the input signal varying, and mathematically I can just multiply these two and get my output signal, desired output signal. But when we are trying to implement this in the circuit, ultimately we have the amplifier input. Suppose this is your feedback amplifier with the feedback component included within this triangle. So we are trying to have this implementation using cross couple switches, and we have seen that during the first phase phi 1, the input gets connected to the first polarity plus minus, and in the alternate phase phi 2, the signal polarity gets reversed and the signal will be getting connected to the minus plus terminals. And this effectively means that in the phi 1 cycle, the signal over here is getting multiplied by the gain AF, if the closed loop gain is AF. Thus, in the phi 1 cycle it is getting multiplied by AF, and the second cycle phi 2 the signal is getting multiplied by minus AF, and hence we have a plus minus AF multiplication happening on the input signal. And ideally, of course, that would mean that the output signal, if I look at the fully differential output V out plus minus V out minus, that will be just getting chopped accordingly. So, you will have the overall amplifier signal getting chopped. So, this is what we expect. So, if I look at V out plus, this is your V out plus minus V out minus, we expect the input signal, I am assuming this is your V in plus minus V in minus, input signal getting multiplied by this plus minus 1. As a result, every cycle you are getting the output signal changing the polarity in a stepwise fashion. Now, this is a mathematical picture, but if you look at the circuit, of course, circuit cannot have a ideal step like rise and fall time. It will take some finite time to settle to a certain value. So, for example, if I consider one particular time instance where the phase is changing from phi 1 to phi 2, there of course the signal, the input signal is shifting the or reversing the polarity, and within this rise time or within this duration, the output signal should finally settle to A times V in plus minus V in minus. So, if I assume that this is going to act like a step function, so the clock function, assume that clock is the clock which is the phi 1, it is acting like a step function, and it is getting switched at a certain frequency given by Fc 1 kilohertz. So, within the half time period of Fc, assuming 50% duty cycle, within this half time period of Fc, the signal which is coming at the output should be able to settle. So, the output signal finally should be able to settle. If I assume, say, that the amplifier is a single pole system, assume that there is one dominant pole. So, I can represent the amplifier transfer function as 1 upon 1 plus s upon p, where p is the dominant pole, and this is basically representing a single pole RC system. So, I can represent this as an ideal amplifier followed by an RC low pass RC filter. So, I can represent this as a ideal amplifier with gain A and an RC filter where 1 upon RC equal to P. And if I represent the time constant T as say 1 upon P or 1 upon time constant as 1 upon P or RC, we know that this kind of system is going to have overall time domain response given by V naught 1 minus e to the power of minus t upon RC. So, if V naught is the step that is the output is supposed to take, suppose VO is the step that is the output is supposed to take, means it is going to change from V to V plus V naught. So, this is the overall step that is expected in the output as a result of change in the input. So, this I am calling as V naught, and as a result, for a single pole system we have an overall response coming like this, V naught e to the power of minus t upon RC. And if the pole is towards lower frequency or the time constant is larger, then we know that this RC time constant will be worse and the charging will be, or the rising of the signal can be much slower. Likewise, on the other side, when you are going towards the negative phase phi 2, there I expect that the signal will be going down. There also, if the RC time constant is large or the pole is towards low frequency, rather than the signal going down quickly, it will take good amount of time to go down, and it may so happen, if you can see, it may so happen that the signal does not even reach the required value, it does not even reach the final value. If the clock frequency is much larger as compared to the pole frequency, the signal may not be able to reach the final destined value. As a result, the final value that you get is going to be dependent, or it is going to be having nonlinear dependency on the input signal. If your input signal change is smaller, or the delta V that you are seeing over here is smaller, then it will be able to settle more conveniently. But if the delta V input is larger, it will take larger time to settle. or it will not be able to reach the maximum value that is supposed to be there. So, it can lead to non-linearity, and the ideal multiplication function that we are trying to implement, that will not be achieved. So, we would like to have this settling as fast as possible. So, this rise time should be much smaller as compared to the overall half period of the clock. So, I would like my signal to settle much faster. So, within 1, if this is t by 2, I would like the settling time to be close to 1 by 10th of this. So, I would like this settling time t settle within which the signal is settling to the final value. If I call this t settle, the time taken by the signal to reach the final value starting from the sampling instance, I would like this to be at least say to be conservative 1 upon 10 t by 2, and that means the pole frequency will be 10 to 20 times higher as compared to the frequency of the chopper. So, if the pole frequency is higher or the bandwidth of the amplifier, closed loop amplifier is much higher, then the chopped signal at the input and the output finally it will be able to settle properly to the final value. So, that is the reason why we need to choose the pole frequency much higher than the chopping frequency. So, if I assume that the chopping frequency has been taken as 1 kilohertz, that would imply that the amplifier bandwidth would be even larger, maybe at least around 5 to 10 kilohertz, to be more conservative, maybe 20 kilohertz. So, let us stick with a reasonable number 10 kilohertz. So, if FC is 1 kilohertz, let us go for the closed loop amplifier bandwidth as 10 kilohertz. So, we have discussed this briefly while discussing the chopping operation also, that why do we need to have a higher amplifier bandwidth when we go for the chopping operation. So, chopping is helping us in shifting the signal towards higher frequency 1 kilohertz, but the amplifier bandwidth needs to be even higher than that, because the chopping clock is acting like a square pulse, and within that the signal must settle fast enough, and for a good performance I would like my signal to settle within 1/10 of that half period. So, in this case let us choose the amplifier bandwidth to be 10 times FC, let us call it closed loop bandwidth. So, F or bandwidth close, that can be chosen as say 10 kilohertz. So, this is the slightly modified requirement that we have as compared to that we started with, what we started with in the very beginning. In the very beginning we did not consider the concept of 1 upon f noise or chopping, and we started with a naive assumption that yes, your signal frequency is from 0.5 hertz to 100 hertz. So, possibly I can design my amplifier to meet this particular bandwidth. In certain cases where the signal strength is sufficiently large, we may be able to do away with chopping. For example, if you are talking about some biomedical signals which are having much stronger amplitude, rather than few tens of microvolt, they will be having few millivolts at least. So, in that case the signal magnitude is sufficiently large, and even if the frequency content is down to close to even a fraction of hertz, you can do away with chopping. But in cases where the signal magnitude is so low, 10 microvolt or few microvolts, there the 1 upon f noise becomes very serious, and as a result we have to go for the chopping operation. So, in case of the particular application that we targeted, neuropotentials, there of course the signal content, the frequency content is this, but the amplitude is also pretty low, and that would necessitate the use of chopping. If we are talking about some other signals like an ECG signal, for example, there the amplitude coming from the electrode can be pretty significant or pretty large as compared to this, it can be few millivolts. So, there chopping may not be necessary, but for neuropotential acquisition, because of much smaller input amplitude, chopping becomes very important, almost necessary. So, let us now conclude that okay, the closed loop bandwidth is supposed to be 10 kilohertz, and now we need to go for the open loop bandwidth and the gain bandwidth product. So, the gain that was expected was the closed loop gain overall, say we are going for around 10 to the power of 4, that is what we estimated. So, if for example, if you have in the maximum signal amplitude of 100 microvolt and then the closed loop gain is 10 to the power of 4, so the maximum peak to peak swing that you can have at the final stage is going to be around 1 volt So for a 2 volt VDD, 1 volt peak to peak swing can still be tolerable if you design the amplifier properly so that the output stage swing is maximized. Then you can go for a larger output swing, and therefore the overall gain that we are targeting from the amplifier stages and maybe even the filter stages, overall it will be 10 to the power of 4. And then we can divide this gain into 2 stages. So we also discussed the rationale for that. Rather than going for single stage, we can divide it into 2 stages, and one single amplifier was supposed to have a gain of closed loop gain of around 50 to 100. So let us take it to be 100 at the max. More reasonable numbers are 30, 40, 50. So let us be more aggressive. Let us take closed loop gain of around 100 for each stages, and therefore we have the AF which is going to be approximately 1 upon beta equal to 100, and also we have the A naught. And remember, how did A naught come into picture? A naught is determined by the precision required. So the 1 plus A naught beta terms, if you want to ignore that 1 with respect to A naught beta, the overall A naught beta should be at least 100 times higher than 1 if you are going for 1 precision. And therefore here, if I am taking beta equal to 1 upon 100, I would like to have A naught 10 to the power of 4. So this would give me A naught around 10 to the power of 4, such that A naught times beta is greater than at least greater than 100, greater than equal to 100. So that will ensure that you have 1% precision in the term 1 plus A naught beta. When you are ignoring this 1 with respect to A naught beta, you are incurring an error, and that error should be less than 1%. For that, I would like this A naught beta to be greater than 100, greater than or equal to 100. So that will give me the A naught 10 to the power of 4. So from here we have the open loop gain of the amplifier, and we also have the closed loop bandwidth. So from here we can also obtain the open loop, the gain bandwidth product and the open loop bandwidth of the amplifier. So the closed loop bandwidth is targeted to be 10 kilohertz, and we know that closed loop bandwidth 10 kilohertz is going to be equal to open loop bandwidth, sorry, BW. This is going to be open loop bandwidth BW open times 1 plus A beta. 1 is small, so times A beta approximately. So here we have also seen that the A beta is we are choosing it to be around 100, and as a result the open loop bandwidth can be taken as 10 kilohertz divided by 100, and therefore the bandwidth open is around 100 hertz. That is what we looked at. So open loop bandwidth of the amplifier that we are trying to design is around 100 hertz, considering the gain bandwidth product requirement. And also we have the A naught as 10 to the power of 4, and that gives me the gain bandwidth product GB is equal to 10 to the power of 6. So this is our modified set of gain and frequency considerations that we arrived at, considering the chopping operation, considering the 1 by f noise mitigation. So the gain bandwidth product is an important feature of the overall open loop amplifier with which we can begin the design. And now, while looking at the design, we have to recall how does the gain bandwidth product depend upon the circuit parameters of, say, the 2-stage op amp, and from there we can proceed step by step and look at the other parameters like the overall bandwidth and the signal swings, and include them step by step. Also looking at the interface of the circuit with the next stage and the previous stage, we have to estimate the value of the load capacitance, which is going to play a role in determining the capacitance value, compensation capacitance values. So let us start with the required gain bandwidth product of 10 to the power of 6, and of course if you look at the if you look at omega, there will be 2 pi times 10 to the power of 6. In terms of hertz, this is just 10 to the power of 6 hertz. So let us keep it 10 to the power of 6 hertz. And now if I go back to my 2-stage op amp, we have derived the expression for gain bandwidth product, overall bandwidth, the overall small signal gain. So we are going to just use those in order to arrive at the values of transconductance and the compensation capacitors, etc. One of the inputs required to do the calculation will be the load capacitance. What is the load capacitance faced by that amplifier? And towards that end, again we have discussed that the load capacitance ultimately for the overall differential operation depends upon the next stage input capacitance. So you may be having the next stage input capacitance acting as the load capacitance of this stage. So you have in the next stage, once again, you know, remember that this point is going to be AC ground for the another next stage amplifier, and as a result, the overall input capacitance, the overall load capacitance experienced by the stage 1 amplifier, which is built of my 2-stage op amp, is going to be given by the CC, or the C1. So if I call this C1 and call this C2, C1, C2, we know that the overall gain for both these stages will be given by the ratio C1 upon C2. And if I look at this stage, the 2 input points can be treated as AC grounds, or rather they are going to be very close together, they are not going to have any significant signal swing. As a result, these 2 C1 values appear as effective load capacitance for my output point, and therefore whatever is the value of C1, we can take it as a load capacitance. And again, value of C1 depends upon the value of C2 and the gain required. And there, if you remember the discussion that overall gain 100, that would mean a ratio of 100 between these two, and C2 minimum value will be determined by the parasitic capacitance of the amplifier. So if the C2 is sufficiently large as compared to the parasitic capacitance of the transistors, then the gain will be relatively well defined by the ratio of C1 upon C2. If you make C2 too small and it becomes comparable to the parasitic capacitances of the amplifier, then it is the gain precision, or the gain is less precisely defined. So I would like to keep C2 at least a few times, maybe 10 times larger than the parasitic capacitance value, and we saw that maybe 100 femtofarad is a good value for C2. And we have seen that the MOSFET dimension, based on the MOSFET dimension that we have, the overall capacitance that you can get at the output node may be of the order of few tenths of femtofarad. So I am taking around 100 femtofarad for C2, so that it is sufficiently larger than the parasitic capacitances at the output node. And then you have the C1, which again needs to be 100 times the C2, therefore we can keep this of the order of 10 picofarad. So it will be within few picofarad to 10 picofarad. That is the expected range of C1. And in the beginning, we have also discussed that at least for the second stage, we may need to keep the C1 programmable or tunable, because we may need to adjust the gain of the overall amplifier depending upon the input signal strength. So sometimes if the input signal peak to peak is increasing because of the change in the interface property of the electrode and the electronics, then the overall gain over here may need to be reduced. Whereas if the signal strength is reducing, say from 100 microvolt, it is going to 10 microvolt peak to peak. In that case, the overall gain of this amplifier stage may need to be increased. So that depends upon the overall magnitude of the input signal, and we have discussed this reason why we need to increase or decrease the gain, so that we can fully utilize the dynamic range of the ADC. So very briefly, we have discussed in the beginning that the ADC has a fixed input range. I would like to map the final output signal amplified and process output signal to the entire input dynamic range of the ADC. So we will discuss that once we have a discussion on ADC. We will look into the dynamic range concept once again in detail. But if the dynamic range of the ADC is say 1 volt, I would like that the output signal over here is always mapped to that entire 1 volt range, so that the final output peak to peak swing over here is close to 1 volt peak to peak. So if the input signal changes, I need to program the C1, C2, so that depending upon the strength of the input signal over here, I am setting up the gain so that it is mapped to the entire dynamic range of the ADC. So that was the concept. So one of these stages, generally the second stage amplification, is kept programmable.
So this open loop bandwidth, we have to consider all this load capacitance coming or without this capacitance.
Open loop bandwidth, ultimately you have to look at the total, the open loop bandwidth depends upon the critical pole, the P1, which you are trying to compensate and push towards lower frequency. So that P1 is not directly dependent upon the load capacitance as such. So that is dependent upon only the capacitance, the CC, the compensation capacitance, and the gain of the second stage. That is going to determine the open loop bandwidth. So that doesn't have interaction with the
the output stage.
Yeah, so as I said, ratio is determined. So in order to get a certain phase margin, yes, you need a certain ratio between the CC and the CL. So that way it is related. But if I say that how is the bandwidth determined, open loop bandwidth or the 3 dB cutoff frequency of the open loop amplifier, that is determined by CC and the gain of the second stage, CC times A2 times the RO, that gives you the RC time constant of the first stage. So, we have so that basically we can assume that the overall load capacitance CL faced by the first stage is say 10 picofarad. So, this is the CL given to us, and now we can go back and find out the value of GM in terms of the two stage op amp circuit parameter that we have. We have seen that the gain bandwidth product depends upon the GM1 upon CC, where CC is the compensation capacitor, and in order to achieve a 45-degree phase margin, we said that the gain bandwidth product should be equal to the P2, or the second pole should be equal to the gain bandwidth product, which is equal to GM1 upon CC. And what was the second pole value? This is the expression for gain bandwidth product, which is P1 times the open loop bandwidth, if you remember, and this should be equated to the second pole. So, the pole 2 P2 should lie at the 0 dB crossing point, and for that I need to equate it to the gain bandwidth product. That is what we discussed. So, I would like to make this equal to P2. What is P2 value? P2, if you remember, output stage, this is going to be given by CL, the overall load capacitance at the output stage, times the R equivalent at the output stage, that basically becomes 1 upon GM2. So, for the two stage op amp, the R equivalent at the output stage is just 1 upon GM2, and therefore, I just need to make sure GM1 upon CC equal to GM2 upon CL, and that is going to determine my relationship between these two parameters, GM1 and GM2, CC and CL. Also, I would like to have certain power constraints. So, since we are looking at a low power application, I will start with certain power budget for the overall front end amplifier. Say I take the I bias total as 30 microampere for the total amplifier, or say keep it 40 microampere for the total amplifier, and in that case each of the two stages is having 20 microampere each, and that means each branch is going to have 10 microampere. So, it is not necessary to keep the same bias current in all the branches. Like if you have the first stage differential amplifier, second stage common source amplifier, I may choose different bias current for different stages, and we know that the bias current generally in the first stage needs to be higher, or the bias current requirement is higher, and the reason is that we have overall gain requirement as well as noise requirement determined by the GM of the input device, and especially for the noise requirement we need to have a sufficient bias current available in the first stage. So, we can factor this bias current to divide this bias current in an uneven fashion also. We can preserve 30 microampere for the first stage and lower amount of bias current for the second stage, or we can go for equal division also. That is a design decision, and iteratively if I start with say 20 micro division and it finally seems like it does not satisfy the noise criteria, I may have to go back and steal some more bias current from the second stage and divide it, shift it towards the first stage. So, let us say that you can start with 20 microampere bias current for each stage, and this will give me 10 microampere each for both for all the branches, the differential branch as well as the output branch. So, this is a requirement which is given to me from the top level specification. I have estimate of power budget, I want to stick within this, or preferably I would even like to minimize this. If my requirements are well achieved within this limit and I have a lot of margin left for optimization, we may further try to reduce this bias current to save my power consumption. So, suppose this much bias current gives you a much better gain bandwidth product than required and much better bandwidth than required, then definitely you have an option of going down and reducing this bias current further, so that you can save power while satisfying the noise criteria. So, this is a starting value. You have been given a requirement like this, and then it is up to you how low you can go, but you should not cross this, you should not go above this. That is the starting point. So, in the beginning I can try to make the use of the entire power budget that is available to me, and then if it comfortably meets all the specs, then I have the target of minimizing power consumption also. I can go back and try to see how low I can go in terms of this bias current, so that I can minimize my power dissipation overall while maintaining the other specifications, especially the noise and the bandwidth. So, I have say the bias current requirement coming over here, and then I have the overall the CC and CL ratio supposed to be determined considering the overall area. So, if you remember the capacitance C1, they are the largest capacitance over here as compared to C2. This value is much larger, and as a result they are going to be the most area consuming part of the front end amplifier. So, whenever you are going for capacitive feedback or even resistive feedback, the larger passive component takes the maximum amount of area. So, if you look at the physical design of the chip, this C1 the area will be much larger than all the other transistors area that are building this amplifier, and therefore it would be prudent to minimize the values of the C1 and also the corresponding compensation capacitor. So, compensation capacitor also, if it is close to the C1 or the CL, then again this also becomes a dominant factor, and this also consumes a lot of area. So, it would be important to minimize both these areas, both these values CL and CC. Now, CL we have already estimated that okay, for a well defined gain and a gain of 10 to the power of 4 overall, and hence a closed loop gain of around 10 to the power of 2 for one stage, I need C2 upon C1 ratio of 100, and as a result I am going for a minimum possible value of C2 100 femtofarad, so that is to minimize C1. So, C1 is given to me, this is the minimum value of C1 possibly I can have to satisfy my range of gain value that I want. And then once C1 is determined, I am looking at these values. Now, CC and CL. So, CL is basically nothing else but the C1 of the next stage. So, I can say CL is equal to C1, which is equal to 10 picofarad, and then if I make CC equal to C1, then again I am doubling the area, just doubling the area, because CC 10 picofarad means twice the area. Now, if I want to be a little bit more conservative, I would like to push the CC value to a smaller number, so that I can save area. So, I will like to make it say 5 picofarad. In that case, only 50% additional area is being used. If I go a little bit more aggressive, make it 2 picofarad, then of course the area consumed by this CC is significantly less as compared to the C1. So, let us start with a estimate that okay, let us keep CC equal to 50% of C1, so that it is not adding more than 50% area as compared to C1. Definitely one of the important design constraint can be to minimize the CC as well, and that again translates to the ratio of GM1 GM2 and sizing of the GM1 GM2 transistors and so on. So, if the area is very critical and every micrometer square is going to count in your design, therefore, in those cases you would like to be more aggressive over here. I would like to be more 0.1 times C1 or 0.2 times C1, because I worry about every micrometer square. I have to pack so many channels. I have to pack maybe several tens of such channels to acquire multi-channel potential data. So, in that case I will be really conservative about area, and there I would like to be more aggressive. I will choose a smaller number over here, so that the overall area can be as minimum as possible. For the time being, let us just keep this CC as 0.5 times C1, and as a result I have CC value determined, and then I have the GM1 GM2 ratios individually determined, and also the individual values of GM1 and GM2 can be determined from this equation, right. So, once I have determined the C1 10 picofarad, and I also have the ratio C1 and CC, I have basically the value of GM2 as well as GM1 known. So, from here I can get the value of GM1, which is the gain bandwidth product times CC, and likewise GM2, which is, or let me stick to the round numbers, GM2 is equal to gain bandwidth product times CL, which is 0.5 times CC. And now once we have say the GM1 GM2 value determined and the bias current of the two stages determined, I also have the value of W by L estimated, because GM1 GM2 determined by the ID1, if I call M1 as the input device, ID1 times W by L1, and this is proportional to ID2 times W by L2. So, I have these two products determined, and as a result, since I have already chosen ID1 ID2 to be around 20 micro each, I can look at the W by L ratios of these two devices. So, W by L of the W by L of the first stage, since it is just double that of the the second stage, I would need 4 times larger W by L over there to meet the criteria. So, that is giving me the information of W by L for the input device of the first stage and input device of the second stage. So, this is the W by L ratio. We have not yet determined the W and the L, but at least the W by L ratio estimate is here for the input devices of the first stage and the second stage. Now, so we can take 2 minutes break. After that, we will resume the discussion.